But okay. So what we're going to start discussing waves and instabilities. And so this is usually the topic that we cover last because it's also the most, let's say, analytically it's the most involved, but it's also an extremely interesting one. So waves and instabilities are really at the core of fluid mechanics. I mean, it's not my specialty. It's not really what I do as a researcher, but in a lot of fields, concept of waves and instabilities are inherently linked to the study of fluid mechanics. And so for all of you who are in marine technology or later on in technology, you see instabilities in fluids all the time. We started discussing them. So when we looked at the lubrication approximation and we saw the droplets forming, that's a form of instability. The interface could remain flat, but eventually destabilizes and you have little droplets form. That is an instability. What we discussed at the very beginning of the class, when you have a shear layer and you start seeing those vortices in the shear layer forming when you have a shear flow, which is stabilized by stratification, but you have a shear that is destabilizing. This is also the Kelvin-Helmholtz instability. You see that in atmospheric flows, you have a lot of instabilities. So we'll discuss those. And we'll start we'll have 2 or 3 lectures, so 3 lectures on that. And today what we'll discuss are gravity waves. So we'll first discuss waves, and then waves and instabilities. And in your book that corresponds to chapter 8 and to chapter 11. So today we'll discuss waves, but you'll see that the equations and the study will be quite similar. So this is Kundu chapter 8.1 to 8.3. That's in principle what we'll discuss today. Now, before we do that, and before you get overwhelmed, the important thing is to not get overwhelmed by the mathematics. So I'll just do a brief reminder of some mathematics, and especially on some notations. And it's a bit confusing because you've seen that so many times in so many different contexts. You have seen some of that in your classes on differential calculus, right? And then you'll probably see it again a lot in controls, because in controls also usually you want to design a control sometimes which will stabilize an unstable system where you're trying to get your roots. If you remember, you don't want to get the roots in the right hand side of the plane. You don't want to have roots with a real part. I don't know if you remember that, but we'll see that again. But so you see that in so many different contexts, and at some point you become confused. So let me just really take the basics. There are a few notations that you need to remember. The first one will be the wavelength. So this is an important one for today, the wavelength. And that is, if you have, say, a periodic function, let's say this is my function here. And usually you talk about a wavelength when your function is a function of position. Right? You wouldn't talk about wavelength if it was a function of time. For a function of time, you would talk about a period. But for a function of space, so if this is actually position, so say this is x, and this is y, and that is the shape of an interface, for instance, the wavelength will be this distance here. It's the length of one wave, of one period. This is the wavelength. Maybe this is silly to emphasize, but it has dimensions of a length. So for a cosine, for instance, a cosine, oftentimes you think about it as a function of time. Here I want to think of it as a function of space, and in that case, as this function could be, for instance, a cosine of 2 pi divided by lambda times x. So this function here would be this cosine. Right? X equals 0, you are at cosine equals 0. Cosine equals 1, sorry. No, I did it the wrong way. So x equals 0 will be here. X equals lambda is going to be here, the next period, when the cosine is again equal to 1. Yeah, you see it here. When x equals 0, the cosine is equal to 1. When x equals lambda, cosine 2 pi is also equal to 1. That's your wavelength. So the wavelength is sometimes expressed as the wavelength. It's sometimes expressed as a wave number. So here, sometimes you'll see that as a k, and that is the wave number. So think, large lambdas means large wavelength, means small wave number. If you have a high wave number, that means you have lots of wave. That means that the wavelength is short. It's just one is one over the other, essentially. So the wave, let me just write, the wave number is equal to 2 pi divided by lambda. Here, this would be the wave number. This would be the wave length. Okay, so remember, always remember, high wave number, that means you have lots of wave, short wavelength. Okay? That's the first thing. Now, the second thing is a wave speed, which is usually called c. Now, usually waves, if you've watched some water, then you would know that your wave usually doesn't stay fixed like this in time. That would be very weird. Your wave just changes in time. It propagates. So it's waves are inherently unstable, unsteady. I shouldn't say unstable. I should say unsteady. And the speed at which a wave moves, that's going to be called a wave speed. So if I have the same wave, now again, I want to think you of this as a cosine as a function of x. Let me write it here. So this is cosine. I'm going to write kx, but I could as well just write cosine of 2 pi divided by lambda x. That's the same thing, yeah? But I'm going to write kx now. So if this wave, just say the same wave is propagating, so just imagine it's moving to the right. So later on, my wave is here. Right? So black is at time equals 0. And blue is at time t. Then you can think of the wave speed as the speed at which it took, so it moved over this distance, my wave. Let me call this, for instance, x. I'll call it for now xt, right? And so it moved over this distance during a time t, so it has a certain velocity. This velocity is the wave speed. You can think of that as the wave speed. And so xt is going to be equal to the velocity times the time elapsed, so ct. So you could take this as a definition for c, right? So the c here will be your wave speed. Now, if I want to write as a function of position and time where my wave is, right? So cosine kx, this was my wave at time 0, right? Anyone sees here what the wave will be at time t? Huh? Okay, minus ct, you said? Huh? Yeah, minus ct. So you can think of it as really k x minus x at t, right? So what was 0 at time 0 is now at xt, right? And so in a way, this is just cosine kx minus ct. So this function here would represent that wave form, which remains the same, but which is traveling to the right at the velocity c. Yeah, do you guys see that? So we'll see that a lot today. Okay. So let me write something else then. Oh, hold on. This is k. Sorry, I forgot the parenthesis here. So kx minus ct. Now let's, for the notations, sometimes you will see that Kc, K times C, will be written as omega. Now let's see what Kc is equal to. Kc is equal to 2 pi divided by lambda C. So this is 2 pi divided by the wavelength divided by the wave speed, which that would be this is the frequency. Yeah? So C divided by lambda is your frequency. So you see that omega is your angular frequency. This omega here is your angular frequency. So this function here I can also write as cosine kx minus omega t. Right? And now k is your wave number, omega is your angular frequency. All right. Now the other thing which you should notice here is that we'll be dealing a lot with cosines, periodic functions, and cosines are great because they're real functions and you're very familiar with them. But analytically, when you're doing stuff, they're a bit more. They're not so. You carry harder, like more involved notations. So usually, what people would do is instead of that, they will go to complex notations for cosines, because it's easier analytically to derive an exponential than a cosine. Like your cosine, you always have to think, now my cosine becomes a sine with a minus sign, my sine becomes a cosine, so it's complicated, whereas differentiating exponentials is easy. So this is why usually instead of working with cosines, you would work with complex exponential. Right, so we will work with that, exponential I to the kx minus omega t. It's the same as this cosine. You can think of this cosine as being the real part of that. Right? It's just the real part. And the reason why you do that is because literally when you do the analytics, it's easier to play around with exponentials than to play around with cosines. You don't want to remember that I differentiated once, now it's a sine, now it's a cosine. This is just complicated. You don't want that. Okay, so this is complex number. And now let's generalize a bit. And we're going to generalize this notation. So right now, what we discussed is k, of course, it's a real number. It has dimensions of length, right? So it is the wavelength of this wave. It's a real number. But now I want you to all of a sudden think about omega, not necessarily as just a real number, but as a complex number. Right? And so this is where you'll see the link with your class and controls. Now let's think what would happen. You have the same functional form. So you have this function, which looks like a wave which is propagating. But let's assume now that omega is not just a real number, but of course it has a real part, but let's assume it also could have an imaginary part. Right? If you have that, then your function is going to look like exponential I kx. The real part is still going to look very much like, all of this is still going to look very much the same as before. But then you have a plus I times the imaginary part of omega, and that will give you an I squared, so a minus I squared imaginary part of omega times t. So you have plus the imaginary part of omega times t, right? Do you see that? I have an I squared, you become a minus 1, I have the minus omega, the minus imaginary part of omega, so you have a plus imaginary omega times t. So everything will look the same, so this exponential I kx minus the real part of omega t. This here looks like your wave, it's the same thing as before, but now all of a sudden you have this. You have this here. Yeah? The imaginary part of omega is a real number. This is a number. So you have that term. Whenever you have a term like that, you always have to pause because it's going to be dramatic. You know? Either the imaginary part of omega is going to be positive, in which case this thing is going to blow up to infinity with time. or the imaginary part of omega is going to be negative, in which case you will never see the wave which is on the left-hand side. Right, so here you have a wave with a certain wavelength. Right? I have a wave with a certain wavelength which travels at a certain speed. If the imaginary part of omega here is positive, this thing is going to blow up. You're going to see it dramatically, really quickly. Okay? You're going to see that wavelength a lot because it's going to go to infinity. If the imaginary part of omega is negative, then you will never see this wave because the amplitude is just always going to decay to zero. Yeah? So let me just summarize that. So number one, let's imagine that if the imaginary part of omega is equal to zero, let's first say that. That means that omega is real. Right? Then you just have waves. Right? This here is equal to zero. We have the same thing as before. We just have a wave. If the imaginary part of omega is larger than zero, then we have an exponential blow up. Okay, so this wave here, this wave grows to infinity. And when the imaginary part is negative, you have an exponential decay, which means that this wave here disappears. The amplitude of this wave is just going to go to zero. Now, whenever you'll deal with exponential ikx omega t stuff, usually this is because we're looking at the linear regime. We're looking at small perturbation in the linear regime. So this is the same sort of approximation which you did when you're doing solid mechanics, when you looked at buckling. Right? You looked at buckling, which is an instability, and you looked in the linear regime. So this is the same thing here. We look in the linear regime. As soon as your wave, you have an exponential. If your wave, if you have an instability, so if this thing grows, so if the imaginary part of omega is positive, then you will go from a small thing to a big thing, and then of course, as soon as it becomes big, all your assumptions about it being small are wrong. And then you have nonlinear waves interactions, and so at some point, the amplitude will be limited by some physical factor. You've been in the ocean, you know that your waves don't go to the sky. At some point, there's a limiting factor, but the limiting factor is the nonlinearities. At some point, your assumptions of linearity don't work anymore, and you have to go back and revisit, and then the equations become more complicated. But in this class, and usually when you're looking at the stability of a problem, the first thing you look at is linear stability. Okay. Okay, and then my last, the last mathematical reminder is on linear ODEs. And so what I want you to remember is just the simplest first order linear ODE. Whenever you see that, you know that your solution is going to be an exponential alpha t. If this prime here relates to a derivative in time. Huh? Okay, so the first thing you do whenever you see a first order linear equation like that, you look at the sign of alpha, because it's going to be, both cases are dramatic. If it's positive, it goes dramatically to infinity. If it's negative, it goes dramatically to zero. That's why exponentials are so dramatic. They either blow up dramatically or they just damp dramatically. So you're either going to see it a lot because it goes to infinity, or you're just never going to see it because it goes to zero dramatically. Yeah. So this is a first order ODE, and then you have second order ODEs. So let's think about a function of time. I'm going to directly do that. Of course, you could have those two ODEs for functions of times and functions of a spatial variable, but usually if you have a function of time, then you would have an f double prime equals to minus omega squared f, in which case your solution is always a periodic function. So your solution will be cosines omega t and sines omega t. And if you have the same equation but with a plus sign here, in that case, let me not write omega squared but k, the wave number instead. So here I'm thinking about f as a function of space. Then the solution are hyperbolic cosines and hyperbolic sines. Okay? I'm just changing the, because usually you'll see cosines and sines mostly as functions of times, not always, but oftentimes. And for space you'll see, but that's not true. I'm just mixing the notation so that you realize that sometimes you'll see the same equation, but your variable is either time or is either space. Okay? Yeah? So the first definition we'll need today, the rest we'll need after the break. So after the break, of course you will have had things happen to to you in the meantime. You will have forgotten maybe some of it. So if you can refresh your memory on those, like, it's not too much, but you really need to be sharp on those definitions, because otherwise you'll get lost in the lecture quite quickly. Okay? Good. And so with that, we'll start discussing gravity waves. So for that, literally think about anything you see at a free interface when you have, say, a denser layer on the bottom and a lighter layer on top. Okay, so we're in the case now where, well, you could say you have a stratification, but not really. Just to say a two-layer flow, and it is stable. At this point, we're not talking stability. We'll do that when we come back. And it is stable because the heavier fluid is on the bottom. Right? So let's start with this, and within the same framework we could do internal waves, but I won't have time to discuss internal waves. So we only look at interfaces. Think about the water in your bathtub. Think about the water in the ocean. You can think about the water in a thin layer in your sink, or also, I don't know if you were a kid, but sometimes you're in a kiddie pool and you see like flowing, like a thin layer of flow flowing down an incline. You also see waves there. They look a bit different because they're very flat, and we will see them propagate. So that's the same. Those are the same equation. We're going to look at all of these problems. Okay. So we have an interface. Let me put this interface at z equals 0. We have a denser fluid here. We have a lighter fluid. And we have a denser fluid. And then we have the bottom. That could be now the bottom of the ocean, or this is the bottom of your sink, or it's the bottom of your kiddie pool. It's just the bottom. Let's say the bottom here is at z equals to minus h. Now there is one thing which you always have to remember, is that an interface or anything is never fully flat. There are always disturbances in the fluid. You could think of just wind. Someone passes by, a boat passes by, or you just threw a rock in the puddle, or something will always tend to destabilize your interface. Right? And so the question is now, is that going to go back to flat, or is any disturbance going to grow dramatically, or is it going to become a wave that will propagate? Okay? So the interface is always disturbed, and even when you're looking at a free interface, say in microfluidics where there is no wind, nothing, then there's thermal fluctuations. You always have molecules that have certain kinetic energy that like bump into each other. So that thermal, that KT, just the KT, will always destabilize also an interface. So you always have fluctuations. So an interface is never completely flat. There's always something which could potentially destabilize the interface. Usually this thing is random. So you may destabilize any sort of wavelength. You can just think about an interface as being disturbed in all wavelengths, and the question is that which is the wavelength I'm going to see, or what happens to waves of a certain wavelength? Do these propagate? Do these increase? Do these decrease in amplitude? So that's usually whenever you see a flat interface, that's sort of an equilibrium position. Never think of that as fully flat. There's always a possibility that it's in an unstable equilibrium and that some waves will grow or propagate. Yeah. So we'll start with that, and so therefore we'll have a little disturbance. We'll think about interfacial deformation. And here I'm going to keep the same notation as what we started with at the very beginning of the lecture, of the semester, sorry, in September. So we'll think about this interface shape, we'll call it H. So then again, here you expect that your kinematic boundary condition at the boundary, at the interface is going to be, the partial H over partial T equals U, blah, blah, the one that we derived at the very beginning when we looked at material derivatives. Okay, so just make a note. Here, you could think of the interface is destabilized, say, by wind blowing. This is for the case of air, for the ocean, for instance, or by a boat passing by, or it could be also just destabilized if it's at a small scale by anything, right? Your bottom may not be entirely flat. There might be obstacles, but at a very small scale, it could be even destabilized by thermal fluctuations. It will always be destabilized. Now here, for today, we assume that fluid 1 is air. Right, so we'll assume that the density is 0, very small density. We don't really care about the flow in the air layer. If you were doing an internal wave, right, so you're looking at a 2 stratification with a heavier, say, salty fluid on the bottom, at the bottom of the sea, and a more freshwater layer on top, and you're looking at waves at this interface, right, then you would need to consider the 2 densities, but we won't do that. So today we assume the fluid 1 to be air, and so only look at fluid 2, right, and we'll only focus on your everyday experience with those kind of interfaces, so the lake, the ocean, in which case usually the flow, you will be able to assume that the flow is inviscid because it's large. The Reynolds number will be quite large. Okay, so we'll look at typical Reynolds number which are large, where inviscid theory holds. Okay. Okay, and so now we're going to put that into equations, and especially what we are interested in is to see how do the waves propagate. And so if I start with a wave of a certain wavelength, how does it propagate? And usually what you are mostly interested in is when you look at your wave speed, how does your wave speed depend on your wavelength, right? This is the important thing. We look at different speed waves. They can propagate at different velocities, but that velocity at which they propagate may depend on the wavelength. When you have that, this is called dispersion relation, and that is the key of studying wave. Right? Wave dynamics, you always want to know how the relationship between your wave speed and your wavelength, or you could also write it as a wave number as a function of your wavelength. Right? So that's always what we are aiming for. So don't be surprised. What we are aiming for is just simply a relationship between, if I have a certain wave of a certain wavelength, at which velocity does that particular wave propagate? That's what we are after. So let's write the governing equations. Okay, so the first thing that we'll do is, well, actually I wrote it before, 5 points. Number 1 is we'll put ourselves in the framework of inviscid theory. Number 2, when you do that, usually, so here, because it's wave, it's a bit less crucial, but when we'll discuss instabilities, you always have to do that, so we'll do that here as well. You discuss an equilibrium state. Right? You have to first determine an equilibrium state. Right? So you have to find the simplest solution when you have no wave. Now, what is the simplest solution here where you have no wave? You have just a two-layer flow, which is what happens most of the time in your bathtub. If you had to solve Navier-Stokes equation for that problem, and I'm asking you to find one solution, what would that solution be? You see that solution every day in your glass of water, right? Exactly. Yeah, the H is 0, and there is no flow. Okay, it could be as simple as that. In that case, this is going to be our equilibrium state. H of x and t equals 0. The velocity field u, v, so my velocity vector, equal to 0. This is our base solution. Now, if you think, for instance, of the problem we discussed for the paint, when you look at the formation of the droplets, we discussed you have this bulge forming. Now, this bulge advancing will be your equilibrium solution, and then you would look for the instability in this direction. How do the droplets form? So your equilibrium solution or your base is not always as trivial as nothing is moving. Right? So this is really we're starting simple. You'll see when we'll discuss Kelvin-Helmholtz instabilities after the break that sometimes it's a bit less trivial. It's always the easiest part, but but in that case it's particularly simple. Huh? Now it's clear that this satisfies satisfies our equation. In particular, this is an irrotational flow. Obviously, there is no velocity. U is equal to 0, so the curl of U clearly here is equal to 0, right? So my equilibrium solution is an irrotational flow. Now the good thing is that if we put ourselves now in the context of inviscid flow theory, right, that means that what boundary condition are we going to impose? We'll discuss that later. What boundary condition do we have to impose on the bottom seawall or on the bottom of our bath? Just a no penetration boundary condition, and we cannot impose a no slip boundary condition. Therefore, there is no mechanism that we'll introduce that can create vorticity. And therefore, since we started with a flow which at time 0, our equilibrium state is irrotational, we know that the flow is going to stay irrotational for all times. So we can assume the flow to be rotational, and therefore we'll express everything not in terms of a velocity field, but we express everything in terms of a potential. Yeah, so we're back to actually, so now we're neglecting the effect of viscosity again, and we're back to ideal flows. So the flow is irrotational, plus we assume inviscid flow theory, right, and therefore the flow remains irrotational. And so if the flow remains irrotational, that's point 3, we can use potential flow theory. So we'll use potential flow theory that means that we'll assume the velocity in the water layer to derive from a potential phi. Yeah? And in particular, this potential satisfies the Laplace equation. We'll assume that we have an ideal flow. Yeah? So we'll try to find a solution to the velocity field with those variables. Okay, and now so we have to solve for this is we have to solve for the potential, and then we have to solve it subject to our boundary conditions. Is that number 4 or number 5? 4. So what are our boundary conditions? Our boundary conditions on the bottom is going to be what? So at z equals minus h, which is the bottom of the C, which is the bottom of our container, we have no penetration boundary condition. So we have w, the velocity in the z direction, right? So now, again, this is always a bit complicated because we really, gravity is important. So just to emphasize that, I'm going to call this axis x and this axis z. So really just to emphasize that this is, the direction is really important. This is really the horizontal direction, and gravity is pointing in the minus z direction. So we want w at z equals minus h to be equal to 0. We won't look at things in terms of w, we'll look at the potentials. So my equation is going to be, in terms of the potential, what is w in terms of the potential? It's not a trick question. No. So what is the relationship between the velocity and the potential? Huh? The partial differential. It's the gradient. Yeah. Remember, my velocity u, by definition, is the gradient of the potential. Huh? So if I don't want, this is my boundary condition, it's fine. You can write w equals 0, but eventually I'll just play with the potential. So you may want to write in terms of the potential. So that will be partial phi divided by partial z at z equals minus h. We want that to be equal to 0. Yeah? Agreed? What is the boundary condition at the surface? Right? So at z equals to 0, we will have, well, actually, it's not really at z equals 0. Yeah, it's at the surface, we'll have to impose the kinematic boundary condition. So this one, you may remember, we derived, I think, when we first discussed material derivatives. Yeah? So it's going to be partial h over partial t plus u partial h over partial x is equal to partial w, I think. I have a few notes. Let me see. W. This is the kinematic boundary condition. So I have this one, and then we have something else. Oh yeah. Okay, and then so here we've said everything about the kinematics, but we need to say something about what other boundary condition are we going to need to impose. So have we said anything about momentum balance here? No, we haven't. No. So actually, what form of the momentum balance statement are we going to use here? Huh?
No shear stress?
Okay, so there is no shear stress at the interface. That's true. The thing is, so this is absolutely true, but I'm just going to put it in parentheses. Why? Because if you put yourself in the frame of reference if you put yourself in viscid flow theory, then there would be no mechanism to have shear stress at the interface. Right? The no shear stress in terms of stress boundary condition is similar to the no slip boundary condition. So even if there was shear, even if you wanted to impose shear, if you assume you have an inviscid flow, you cannot mathematically impose that boundary condition. Your shear stress is a force balance in the tangential direction, but if you don't have shear, if you don't have viscosity in your fluid, then there is nothing in the fluid that can sustain a shear, that can just push against a shear force. Yeah, you see? So this is, in terms of stress boundary condition, the no shear you can never impose if you have an implicit flow. We discussed that in boundary conditions. So so shear stress boundary condition and no slip you can only impose when you have viscosity. And we have no viscosity, then you impose a no penetration. But then the other one that you need to impose is which one? The normal stress boundary condition. Yeah. So no shear stress boundary condition. This is true, but we assume an implicit flow. Okay, and so the boundary condition we have to impose is the normal stress boundary condition. And so who said normal stress boundary? It was coming from here. That was you. Yeah. So what is that boundary condition then? It has to do with which quantity? With pressure, yeah. Let me go back here. It's going to have to do with the pressure jump at the interface. So we have P atmospheric here, and we have P, say, at Z equals H right underneath, right? And that difference of pressure depends on times surface tension. Exactly, yeah. So this is where, of course, if you forget the normal stress boundary condition, then you'll never have surface tension in your equation. But it could be, especially if you're at a very small scale, that at some point surface tension becomes important, because surface tension will not let the waves happen. They want to flatten the waves. So the normal stress boundary condition will be written P atmosphere minus P at, say, Z equals H is equal to the radius of curvature. So the radius of curvature, remember, it's a curvature. It's 1 over the radius of curvature. It is the curvature. So it's the curvature times the surface tension. So I have surface tension, and if I'm assuming everything to be small, if I'm assuming the surface deformation to be really small, what is the curvature? It's the second derivative of the function. It's H. Second partial of H with respect to X. I can write it as this as well. Yeah, that's going to be your curvature. Now, if you write like this, it's always important that you can justify your signs. So, do you have a negative sign or do you have not a negative sign? This is a review. Actually, I have 2 questions. And actually, I thought a lot less of you would come. So how do you say? To thank those that come, I have leftovers from Halloween, and so whoever can give me the right answer with the right justification gets this. So is there here a negative sign or a plus sign, and why? Yes. Think fast. Think fast.
Pressure, let's see, is H is larger than
So now you said negative, huh? So we have to do it. So we'll see if you're right or not. Huh? So you have to first think, this is my function of x, right? So my interface is going, so you said what again?
Because the pressure is H,
yeah,
larger than P atmosphere.
In which case is it going to be larger? When the wave is like what? Okay, I think well you may have the right sign, but you don't have the right explanation. So I give someone else a chance. Yes?
If the double derivative is positive.
If the what?
If the double derivative is positive.
If the second, so then what do you have?
Then we have an upward curvature.
If the second derivative is positive, then you have that. Huh? Just think about a paraboloid. Yeah? So this is your function. If A is positive, your second derivative is positive. If A is positive, your parabola looks like this. Yeah, and then
P atmosphere should be greater.
your P atmospheric should be greater. Yeah,
Positive sign.
so it's a positive sign. Did you see? So if your curvature, if this number is positive, right, this is because you will have a function which looks like that locally, and therefore, in that case, you know that P atmosphere has to be larger than P here. Yeah? You know it. And therefore this is positive, and this is positive, therefore there is no negative sign. It was a plus sign. Okay. So you have a normal stress boundary conditions. It's great. Now the last thing we're missing is do we have a momentum? Did we make a statement of momentum equation? Of momentum balance? Have we? At this point? No? Which one do we need to use? Which one do we need to use? If I were you, I would just raise my hand. But maybe you're not, 5 years old, so. Which statement of momentum balance do you do? That's not enough. That's still not enough. Huh? Unsteady, but you said that? No, someone else. Who said that? You said it?
Yeah, I got guessed that.
Yeah, unsteady Bernoulli. It's a wave. It's unsteady, right? It's an invisive flow, and it's a wave. Things are going to change. You see it under your eyes. It's a very unsteady flow, so it's unsteady Bernoulli. There we go. Okay, I have a last one actually for you. So if you want to be so our statement of momentum balance is going to be unsteady Bernoulli. I put one too many i's. Just get rid of that one. So we'll have partial phi partial t plus pressure plus 1/2 rho u squared. Now do I add this or not? Do I add this or not? Yes, right? If you don't add this, then you killed gravity. You don't want to do that. Is equal to a constant. Yes, you have to add this. This is the terms that will actually, give you the balance on your wave. Right? If something gets high, then here, then you know that the pressure here is going to increase, and that's also this is stabilizing mechanism. All right, so we have everything, but the one thing which I wonder now is, you can see everything together, but have we made now a statement of mass conservation or not? And if yes, where is it? That's the last one. Yes? Yeah. Okay. Yes and no. So of course the no penetration boundary condition and the kinematic boundary condition are the statement of mass conservation at the boundary. Okay, but this is not what I was thinking. I was thinking like a statement, the no penetration and the kinematic boundary condition. Those are derived from mass conservation at the boundaries. We're essentially saying no water is leaving through the interface and no water is leaving through the bottom of the sea. So it is, but this is not what the question I was asking for. And the question I was asking for, like, have we made a statement of mass conservation in the bulk of the fluid? Because it's always good when you see all of these equations again to remember where they're coming from, right? Because otherwise you get lost, you forget. Have I made this statement or not? So have we made it? So let me remind you. So we made all of these equations here. Is any of these mass conservation? It is buried in what? Yes. Where? Which one? Exactly. Yeah. It's here. This equation is your mass conservation. We assume we have an irrotational flow, so U derives more potential. So U is, and this is just the divergence of U equals to 0. Right? When you assume your potential to be Laplacian, this is when you say you have mass conservation. Yeah? Okay, so I think we're done for the first hour, and the next hour we'll just be deriving, solving these equations. Yeah.
Yeah. Of you used actually this one for
Here.
This.
Yeah, it's the same.
Yeah. Okay.
This is the norm. So here you have there's a summation.
Yeah.
Right.
Yeah, I understand. But then it's more clear. Then I think that we used the W for U, isn't it?
So no,
So-
U here. No, U is here. This here is the sum. Is right. So this is squared plus partial phi squared plus. This is that. This
Okay.
is the same.
Yeah.
Right? You're taking it's U squared plus V squared plus W squared.
Yeah.
It's the norm of the velocity. Yeah.
And for in this case where because what's then actually is the phi. This one.
This is the potential.
Yeah, I know.
Because
But in this
the gradient.
case, because we got this one.
Yeah. So your gradient. This is the definition. Right? That means that U is equal partial phi partial x, V is partial phi partial y, and W is partial phi partial z. It's a gradient. Huh?
Yeah, I know.
Yeah. So here W is partial phi partial z.
It's 0. Okay.
Yeah.
And this
At,
one.
it's 0 only at the bottom. Huh?
Yeah.
This is the boundary condition.
Yeah. And here we can take it everywhere we want.
Yes,
Because
of
this
course.
is from,
this is it's not the target. This is the momentum equation we're writing in the book. This is Navier-Stokes.
Yeah.
Here you are at the boundary.
Yeah.
Here you are in the fluid.
Yeah, you're right one at the ball.
This is in the fluid, eh?
Yeah, clear.
And this here, yeah, okay.
Ja.
Excuse me.
Yeah.
Just had a. Is your recording still on?
Sorry?
Is the recording still on?
I don't know.
Yeah.
Is there?
Yeah, it's still on.
Yeah, well, I can try, I don't know.
You're recording. You're recording.
Oh, sorry, I'm recording, yeah.